No, it's called a postulate because we're not going to prove it's true. It's just assumed that it is true. And what else does it mean by labeling it postulate instead of an axiom? Max? Right, so it's specific to this planar geometry. It's this two-dimensional geometry that we're going to talk about. And here's what the segment addition postulate says. It says that if you have a segment, and we'll call it segment AC, where point B lies somewhere in between point A and C on that same line, then the following relationships hold true. Again, notice I used the plural. There's three different relationships you need to be aware of. First is the sum of the parts. AB plus BC is equal to the whole AC. So this is the main segment addition postulate relationship. If I designate this in a proof, you can use abbreviations that are accepted for identifying your justifications in a proof. Segment addition is what we will abbreviate segment addition postulate as. So this is the main statement. And segment addition basically means that the sum of the parts is equal to the whole. But you're not always going to want to isolate the whole. You might want to isolate an individual part. So there's two offshoots of this. There's two variations from here that are both also considered segment addition. The first is the part is equal to the whole minus the other part. And the other one is the exact same wording, just the different part. So the part BC in this case is equal to the whole minus the other part. Bless you. These are also called segment addition. Now, when we write these statements, even though we call it segment addition, is there an addition sign in the statement itself? No. So a lot of students mistakenly put segment subtraction. We have not talked about, or we will not introduce any postulates on segment subtraction. These two statements are just another way of stating segment addition. So be aware of that. Make sure you use that carefully. So if we were looking to demonstrate segment addition in a proof. And let's say I take the following segment. Right, so if I gave you, or if I told you that Wx and Yz are equal, and I asked you to prove that Wy is equal to Xz. Okay. Can you demonstrate, or can we demonstrate this relationship? Okay, so again, when I set up my two-column proof, often I'll abbreviate with just S and R. Remember, S stands for statement, R stands for reason. Okay, what would be my very first statement? Julia? Wx and Yz are equal because of given. Okay, so I know that these two segments are equal to each other. Okay, when you attempt to do geometric proofs, here's my suggestion. It doesn't always have to go in this order, but this is the way I think about them. Okay, once I write my given information, I'll look to see, is there any statement that you can make based just on that given information? So if the given information happened to be like x is a midpoint of Wy, then you can make the statement that Wx and Xy are equal because of definition of midpoint. So if you can interpret the given information, you'll do that as your next step. If you are finished, there's no other information you can interpret. What I would do is I'd look at the end state. Okay, are all the elements of the end state introduced in the proof? Is Wy introduced in this proof? No. So my second step would be to introduce those elements. So what do we know about Wy? How can we introduce it? What information do we know about this segment Wy? Well, based on segment addition, it's the sum of what parts? wx plus xy. Okay, so that is segment addition. So segment addition is going to allow us to introduce the whole is equal to the sum of the parts. Okay, so we take care of this element of the end state. It's now introduced in our proof. Okay, what about the next? xz. Is that introduced in our proof yet? No. So we want to introduce xz. And what does xz equal? Xz is equal to xy plus yz. And because it's also segment addition, the whole is equal to the sum of the parts, we can keep it contained in the same step. Okay, anytime you justify two statements with the same reason, as long as they don't rely on any information that falls below those steps, and you can contain them in the same exact step. Okay, and so now, in order for us to, so we have these two elements introduced now. The final thing is to figure out some way to tie them together. Well, in order for wy and xz to be equal, if we knew that the things that they are equal to were equal, then wy and xz would also have to be. So is there a way to make a statement that wx plus xy is equal to yz plus xy? Well, there's a couple ways you can go about doing this. Okay, what if we take this original statement from step 1? Okay, so I'm just going to rewrite wx is equal to yz. What would I have to do to the left side of this equation in order to get this form that I know is equivalent to wy? I have to add xy. So if I add xy to one side of my equation, so again, just take, because I rewrote this equation from step 1, what do I need to do to the other side to balance the equation? Add the same thing. Okay, so sometimes you're adding the exact same thing, as in the case here. I add xy to both sides. Sometimes you're adding equivalence, because again, I could take a relationship and add wx to one side and the equivalent yz to the other side. Okay, and so what process did I use there? What did I do to create this statement from step 1? I used, if equals are added to equals, then the wholes are equal. Addition property. Okay, so you can justify this with the axiom addition property. And then your final step now, what can you replace this whole expression with? What is wx plus xy equal to? wy. And what is yz plus xy equal to? xz. And what justifies that? Anytime you replace things, substitution.